सहना भवतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै ॐ शान्ति शान्ति शान्तिः।
We saw that the ASM chart describes the behavior of the entire system. In our case, in this particular case, it's the master slave JK flip flop. And we also worked out for the given state, okay, what are the possible next states and what are the inputs to be checked and what is the output to be generated. And after assigning code for the state, we also worked out the details of this table. Now what we have is for the present state 0 0, that is for present state A. So now continuing this for the next state B, which is code 0 1, okay. In this the input to be checked is YC, which is 1, the other two are not to be checked. Then the true next state is B itself, which means 0 1 itself, and the false next state is code state C, which is 1 1, and the output being generated in state B is H0 as before. Then work it out for next state, that is state C, code for which is 1 1. In this, the inputs, test inputs to be checked is YK and C, YC 1 1, so it's not YJ, and the true next state is, that is this path 1 0, and the false next state is 1 1, and the output to be generated is H1, not H0. Then we just have one more state, that is state D. It's 1 0, that's the code 1 0. In this, okay, H1 is to be generated, that's the output. YC is the input to be checked, okay, and the true next state is 1 0, the true next state is 1 0, and the false next state is 0 0. Finished? Now whatever we have in this ASM chart, now we have the entire thing in this table. Specifically, you can notice that this set of codes that we have here, okay, this particular one is the one referring to each state separately. So put this code in the memory, right, that is in a read-only memory, put this particular code. So that's our control read-only memory if you are going to implement this entire system using firmware technique. So there are 4 codes corresponding to 4 states, right? That is whatever we have here in this box, that's the code which must go in there. And as before, that's the microword register, which will essentially have the test field, we have seen this in detail earlier. The next field, both true and false fields, and then the output field. Okay, it's nothing new for us. So anytime from the machine, from the memory, you would be reading only one word into this, just one word, maybe this word, which possibly corresponds to state B. Okay, that B. Now here we have the address decoder. We have the address decoder. So essentially, 1 out of these 4 will be selected, and because we have 4 states, we have 2 state variables. So here we'll be having just 2 state variable, called one as A and the other, as I have marked here, as B. Okay, these are the 2 things that go there. So a 2-bit code goes, and 1 out of 4, that's what it is. We will put it as 1 of 4 will be selected. So either this or this or this, 1 out of 4 will be selected, and that will be read in here. Okay, and here we have 2 next fields, true and false. So we will have our multiplexer so as to either select this. What do we have here? Next address, next state, false or true. So one is a true next state, the other is the false next state. Just 2-bit code, right? That's what it is, 2-bit code. One of these, so that is the 2-bit code, which in fact goes to this. That is the 2-bit code we are talking about, A, B. Okay, here you have the 2-bit present state, and we have either this 2-bit true or 2-bit false. That's what it is. Okay, and this, which of these, true or false, which will be selected depending on the test logic. Okay, actually it is some selection logic. Just put it as test logic. Now we know that the test field there are 1, 2, 3. Okay, so essentially from here there will be 3 things which it will indicate. This will indicate which are the inputs to be tested. And what are our inputs? We have Yj is one input, Yk is another input, Yc is another input, and this memory element, right, this also will be using the same. This is nothing but our clock. Okay, Yc is the clock, the same clock will be used here also. Okay, there will be some small change, some phase change, we will not worry about it now, and the outputs will be generated. There are just 2 outputs, right? One is H0 and one is H1, correct? One is H0 and one is H1. Fine. So this whole system has been implemented using these circuits. Now that is our firmware implementation. Why? Because, as I was mentioning earlier, instead of this code, you pull out this memory and put in another code, put in some other code, the behavior of the machine changes. As long as the code is there, this will be the behavior of the machine. Fine. So to start with, assuming if the system is in state A, state A means A will be 0, B will be 0, 0, 0. Okay, assuming it is so, then this would have been 0 0, and 0 0 will correspond to state A, that is this particular one, okay, word 0 0. So this word will be selected, this information will be coming here, and that tells, right, the code corresponding to state A, that is specifically this part. So this will be read into this, and it would say yj and yc are the two to be checked in the present state A. Then depending on whether that combination is 0 or 1, select either true or select the other one, false, and pass on that 2-bit code here as the next state. And in state A, it says generate head 0, that is this will be 1, that will be 0. Fine, finished. Now depending on what this is, the next code will come. If the next code happens to be, say, corresponding to 0 1, so that means the system is moving over to the next state 0 1, then 0 1 will be here, then B will be selected, that is coming here, and so on and so forth, right. Now this in fact is the firmware implementation. Now what is the parallel hardware implementation? That's something, in fact mainly to show that particular one I took up this example, because otherwise we can't discuss this with reference to, say, very complicated systems such as a CPU with many processors. Okay. Again, the starting point of the hardware implementation is again the same thing, ASM chart, because that is the one which describes the behavior of the system. Okay. So similarly, ASM chart we have to have, we start with that. And what is it we have done? We had worked out the details, and we know that there are 4 states, and that with 2 memory elements we can implement this entire machine. So you need to have 2 memory elements, A and B. Now depending upon those memory elements, we have to derive the appropriate equations so that we can design the whole thing. Now what memory elements shall we make use of? The simplest one is to assume a RS latch or a set reset latch. Now what is that? I am assuming on your part that you all know what is an AND logic, OR logic, and NOT logic, and that these are the basic logic gates with which you can implement any system. Now sometimes combining either AND and NOT or and NOT, right, we can also have NAND gates, or the other one is called NOR gates. Now using only NAND gates you can implement a digital system. Similarly, using only NOR gates also you can implement an entire digital system, right. So I'll use NAND gates, okay, and then show you how this whole thing can be implemented. The first requirement which I am saying is I need to first rig up a memory element. Now what is a NAND gate? Well, I'll just work out. The NAND gate, assuming that there are 2 inputs, I will use AB here, so I will use X and Y. A NAND gate which is represented like this, okay, is the one used for the inputs X and Y, that's what I am talking about, inputs, and there are 2 inputs. I am assuming a 2 input NAND gate, and what is the output? The output of this is like this 0 0 with any Boolean variables, 0 0 there with two these things you will be having 2 to the power 2 4 combinations. That's what it is. Okay, this output, what is the output? Basically it says this and then invert, that's what it is. It says and then invert, not is an inversion. So this and this is 0, invert, the output will be 1. This and this will be 0, invert, the output will be 1. This and this will be 0, invert, the output will be 1. This and this 1, invert, the output will be 0. Which means basically for a NAND logic, as long as any input, here we are having 2 inputs, the same thing can be expanded to more than 1 input also. As long as any input is 0, okay, any input, as long as any one input is 0, the output will be 1. That's the main thing. Now, suppose I take one such NAND gate and then connect it up like this. Suppose I take the output of this, connect to this input and take the output of this and connect to this input. Essentially, what I am having is one particular module, okay, with what we call as 2 NAND gates connected back to back, okay, 2 NAND gates connected back to back. What's happening? Just work it out and see. Suppose this input is 0, arbitrarily, we will just say the input is 0. We know one input 0, the output will be 1. So this will be 1. And when this is 1, we can't decide what it is. Agree? Now if it were 0, then this will be 1. On the other hand, if this were 1, this is already 1, this is 1, and so this will be 0. Okay, now see, this is 0. If this were 0, this would have been 1, and if this were 1, this would have been 1, but doesn't alter the output, mainly because even if 1 is 0, the output will be. So this is one stable condition. Now on the other hand, if this were 1, the output will be 0, mainly because this we have assumed as 1, this is 1, this is also 1, and so the output will be 0, and this would have been 0 because same thing, again no problem. So when one input is 0, the other one can be 0 or 1, both ways the output is stable. Now what is that output? That is, this one is always 1, that's what it means, okay. And what did we see? If this were 0, we said this will be 1, right. On the other hand, the other one you take, that is, if this were 1, we said this will be 0. So we will assume this condition. Then we find that this output is 1, this output is 0, complement of it. Okay, good. The same thing holds good for the other one. If this, instead of this, if this were 0 and this were 1, it would have been the other way, because it's symmetrical, right? Now I can use this as a memory element as long as I follow certain restrictions on the input. Why? Remember, recall this. I said if this were 0 instead of 1, I said this would have been 1. Is it not? Now what happens? It's not altering the situation here. This part. This will be 1, anyway still will be. Then both this will be 1, which is not what we want really. Okay? Mainly because a flip-flop, as we had even discussed earlier, that is one output when it is 0, the other output we call it as a complementary output must be just complement of it, that is 1. If one output is 1, the other one must be 0, okay, which is not taking place in this particular one. That's why we say if we follow certain restrictions on the input, okay, then this can be used as a flip-flop in which we can say this, we can just name it this as a true output, okay, this particular one as a true output, and you can use the other one as the complement output. If you want call this true, call the other one complement, either way. Okay. Now let's see, I'll just slightly change this. Suppose I make both the inputs 1, what will happen? If I make both the inputs 1, I can't say anything. What will happen here? We saw that if you make earlier both the inputs 0, right? That's what we started, is it not? This is how we started. We said 0, this is 1, and then I said if this also were 0, this also will be 1. It's not the following this relation, that is true complementing. Both happen to be 1. Now, if I have 0, 0, it's not working, right? If I have 0 and 1 here, yeah, it works nicely. On the other hand, yeah, if I have 1, the other one must be 0. Now what about both being 1? If both are 1, I can't decide. From logic point of view, I don't know, because we don't know what's happening here. So here what we say is the physical conditions will come. One of these possibly is faster, the other one is slower, right? So when one comes, the physical condition will decide what the logical output will be, and depending on what the logical output is, the other one will be decided. One of these will be always faster, because in nature no two creatures are the same. The same thing in devices too. So no two devices, you may call them as same type, so on, whatever it is, IC, given a specific say the type number, say 7400 gate, everything we may talk about, but ultimately when it comes to physical thing, we do not know. One of these will be assuming, okay, will be working faster than the other, and it will assume then correspondingly the output will be decided. That point is, when both are 1 1, we do not know what exactly is happening here, okay, that is important. So if this happens to be 0, then this will be 1, then there is no problem, 1 1, and then this is 0. So we will be using this kind of a thing in which what did we say earlier, both should not be 0, is it not? This is what we worked out. Both the inputs should not be 0. As long as both the inputs are not 0, we can say to it that one output is true, the other is complementary, which behaves very much like a what a flip-flop really is. So we will make use of this particular one and then develop the necessary logic for that. Specifically, this is called a latch, because given an information, it can latch and store it as if it's very much like a flip-flop, and you may work out and then see that it's actually called an S bar R bar latch, okay, because remember while discussing the JK, I was talking about the set and reset. Similarly, there is another one that's called SR latch, but it so happens here it will have to, the input will be an S bar or bar. Just work it out yourself and then you will get that. All right. Good. So we will make use of this S bar or bar latch to implement the state variable A. Similarly, another latch to implement for state variable B, and then work out the relationship. This is the hardware part of it. Okay. I asked you to work out how this particular back-to-back combination of two NAND gates can be used as a memory element. Essentially, the output of this memory element will be a true and a complement. Generally, we use Q and Q bar output. Okay, then it works as a flip-flop. And when I also said that it will be similar to SR, that is set reset flip-flop. Now it so happens that in the set reset flip-flop, either you can have the set input or the reset input. Unlike JK flip-flop, the set reset flip-flop will not accept both being 1. Okay, both being 0, it's fine. Whatever state in which it is, it will stay put. So when the input comes, either set must be on or reset must be on. Both should not be 1. Now when you work out, you will find here that both should not be 0. In this set reset, both should not be 1. Here you will find out that these two inputs both should not be 0. That's why it gets its name S bar or bar latch. Okay. Normally set reset flip flop will be called an SR flip flop. Now what we have here is an S bar or bar latch, mainly because there is no clock or anything, it just depends on the input. Remember, I was talking about an asynchronous system. When the inputs change, the output will immediately change. This is the easiest or the simplest memory element one can have. So we will have two such memory elements, one implementing the state variable A and another implementing the state variable B. We will have that. Now we have to make use of the what's known as Karnaugh maps. Okay, Karnaugh maps to derive the equations, and you may recall whatever you may have learned in switching theory and digital or maybe logic design, okay, or switching theory and digital design. Now the first Karnaugh map I will do for this system itself, which I am calling as state assignment map. Now what is that? Is the starting point of the whole thing. State assignment map, it refers to the ASM chart. Okay, what is that? It just says you have the two variables A and B. We have the two variables A and B. The two variables may take either the value 0 or 1, and for the combination of A being 0 and B being 0, the state is A, small a. That's precisely what it's called state assignment map. This map shows what is the code of, consisting of A and B, that's a variable, for the given state. Okay. Then when A is 0, B is 1, that's here. The state is B, that is small b. And when A is 1, B is 0, that's here. A is 1, B is 0, the state is D. And the other one, both A and B being 1, state is C. Now we have to basically see the two memory cells or memory elements which we will use to implement A and B, how they behave in each of those states. Once we have that, we have the whole system description, right? That's what it is. In other words, we have to generate, why don't we call this the two elements, A and B, the two memory elements. I'll call them as SA or a latch, that is 1, and the other one as SB or B latch. Okay, that said, I have to implement A and B making use of two elements. So one I will call as SA or A latch. Specifically it will be SA bar or A bar latch. Okay, just the bar part of it will drop because we can always complement and get it. So one I will call as SA or A latch, that is the one for the variable A, and the other one for variable B I will just call it as SB or B latch. Now if I develop the Karnaugh maps for these, then that will give me full information about the behavior of the system. Now essentially what it means is I have to generate the SA map from which later on I will develop the SA bar function, and RU map. Okay. Similarly, I will generate for the other two, SB map and RB map. Now what are they? We will work out. So the same thing like before. Okay, same thing for SB also. And RB also. Well, I hope many of you have noticed we started with a system description. Now we are going into the specific state variable behavior. From the system behavior we are going to state variable behavior, and in each state how each of these state variable or the component which implements the state variable behaves. That is what we are going to do. So we start with state A, right, that corresponds to this cell. Okay, all these correspond to the present state A cell. Now we will first work out for variable A. State A, it says the variable A, shall I write down? In the present state A, the variable A, how does it transit? For this link path, the variable A transition is the present state is 0, the next state is also 0. So we talk about a 0 to 0 transition. Then what is the other link path? From here to here, right? That is, again it so happens the variable A, there are only two link paths for state A, either this or this. It so happens in this link path also the variation is only 0 to 0. It means basically in present state A, okay, rather when we say that, what we mean is, if the system is in state A, the state variable A should never get set, right? It should never get set. So the set input of this must be 0. It should never get set. Basically what we are writing down here is the, what is S and R? Is the input, right? What we say is, if the system is in state A, the element which implements state variable A should not get set. That's what it means, right? Can it be reset? Yes, it's already in 0. The reset input comes, doesn't matter. So the reset input is in fact what we call as a don't care. Okay, the set input must be 0. Now let's go to next state. We'll complete for variable A. Go to the next state B. This. So this cell corresponds. After we finish, we'll take up B. Okay, that is state variable B. We'll finish with state variable A. Now state B, there are two link paths. In one it is 0 to 0, in the other one it is 0 to 1. So we don't write it. In state B, the variable A, one link path it is 0 to 0, in the other link path it is 0 to 1. Good. It says the next state of this must be 1 when YC is 0. That's what it is. That is a condition. Okay. When YC is 0, that is, if YC is 0, then the variable A must set to 1. That's what the condition is, input condition is. So we have to see that when the system goes to next state B, the variable A must set only for this condition. That is, the set input must be there only when YC is 0, which means YC bar is 1. The set input must be given or 1. The set input must be 1 for YC bar. We don't know what the condition of YC will be, 0 or 1, right? We don't know what YC will be. It can be 0 or 1. And remember our earlier restrictions that both should not be yes or both should not be both should not be 1. Set and reset both should not be 1. Is it not? Now there is a possibility that this can become 1. So if you happen to have a don't care, which means both can become 1. So we have to see that this must be 0. If it is not 0, when it becomes 1, then we may be violating that condition. Okay? Because a don't care 0 or 1 means it can be 0 or 1. Now if you do the same thing here, then when this becomes 1, we will be violating the original condition. Fine? So the entry here must be 0. Now go to next state C. One link path 1 to 1. Now I don't think I need to work out here. 1 to 1. The other one is 1 to 1 again. It says whatever may be the input condition, the variable A must remain set, which means it should not get reset. It must remain set, right? So 1 to 1 or 1 to 1. What will be the condition? That's what it says. So in state C, that is next state, it should not get reset. So the reset input must be 0. Both, S input can be 1, there is no harm, or 0, which in fact it said don't care, mainly because the next state must be 1. So if set input is 1, the next state will be 1. If it is 0, no harm, right? Anyway, it's already in 1, it will continue to be 1. So it said don't care, but it should not get reset, that's the point. Now go to next state D, that's the last state. For one link path it is 1 to 1, for another one it is 1 to 0, right? Now let us write it down because it's a bit crucial. So one link path, the transition is 1 to 1, 1 to 1. The other one it is 1 to 0 for some condition. What is the condition? If YC is 0, okay? I may say if YC bar is 1, it's all the same. If YC is 0 or YC bar is 1, same thing. So in state D, we have to see that the variable A gets reset for this condition. So the reset input must be generated if YC is 0. In other words, if YC bar is 1. Now the corresponding entry here would be 0, because we do not know whether it's 0 or 1, and to ensure that we don't violate our initial thing, we have ensure that this particular one is 0. Good. Now for variable B, similarly it must be worked out. Alright. So now here we have some corner maps. Maybe many of you may not be familiar with this kind of maps. You may be familiar where you have the entries as 0 or 1 or don't care. But here we have some variable also coming in. So this calls for one discussion. Okay. Now maybe we'll complete the B part of it also, and then learn something so that we can derive the input function from this. Okay. Now B, I'll quickly go through. Go to state A. The transition is 0 to 0 or 0 to 1. 0 to 1 is means set for condition Yj and Yc. So the set input Yj and Yc must be there, right? And the other one must be 0. That is for state A. Go to state B. You have 1 to 1 or 1 to 1, which means it should not be reset. So in state B, we have to see, that is state B, that is this cell. It should not be reset, right? So the reset input must be 0. The SP can be 0 or 1, no problem. Then go to state C for variable B. One, it is 1 to 1, the other is 1 to 0, which means it must reset for this condition. So the reset input must be, we are talking about state C, no? That is this one, this cell. It must get reset. So the reset input must be generated, which is for the condition Yk and Yc, right? For Yk and Yc, this must be reset. Now the last state, that is the D. The D, we have 1 to 1 or 1 to 0. That is variable A. B, we are talking about variable B now. 0 to 0, 0 to 0. That means it should not get set. In state D, it should not get set. Okay. Okay, I'll come to that. State D should not get set. So this is 0. Well, the reset input is don't care, and looks I have not completed this. Since yk and yc is a condition here, this must be 0 based on the logic which we had discussed earlier. Now how do we arrive at the SA and RA function and then subsequently SB and RB function? Once we have them, then we have the logic circuit which must go before this. So there are two such latches, and that function will give us the Boolean expression for SA, RA, SB and RB, or SA bar, RA bar, etc. Agreed? Now can we proceed? There is a problem, mainly because we have what is known as a map entered variable, which many people may not be familiar with. What is that? So we have to study first the problem of how to handle a Karnaugh map with map entered variable. To explain the concept of map entered variable, let us take a simple example with which you may be familiar. I have just taken an example of a function of 3 variables a, b, c, okay, just some arbitrary function. Now when you create a Karnaugh map, the conventional Karnaugh map, you would find that essentially you have 3 entries, that is 3 min terms, 3 entries corresponding to the 3 min terms, and then when you group them together, finally this is the function that you will be getting, correct? So this encirclement actually means a bar and c, okay, that's a yellow one, and this red one encirclement really corresponds to bc, okay, good. Now what is the map entered variable? The map entered variable comes up because we are trying to reduce the size of the map. That is how it comes about. See here, take this map. You find that if you just take this as the axis, then right of this axis the variable b is 1. So this entire area is called B field, because left of this b is 0. So that particular thing correspondingly is called B bar field. Now imagine that about this axis, okay, about this axis, if I fold the map, then this will merge with this will merge with this min term will merge with this min term cell will merge with this, right? What is the effect of that? B merging with B bar, what happens? B vanishes. In other words, what we are doing is, by doing this folding around an axis which identifies the a variable and its variable bar field, the size of the map gets reduced, mainly because we are removing one variable, that particular variable, okay, which the axis identifies. The same thing you can also do. For instance, if you take this axis and fold it, A will vanish, that is what it means. Now reduced Karnaugh map is what you have here, right? Precisely that is what has been done here. We have not yet carried out the entries, we will do that. So B vanishes mainly because about this axis I am folding the map. Now what is the end effect of this? What will be the entries here? Let us work out. So take this. When you fold, this and this merge. This and this merge, I said, right? This cell and this cell. Both have nothing. So correspondingly there will be nothing here too. Nothing actually corresponds to 0. Okay. What about this? So this will merge with this. What is the entry here and what is the entry here? Both are 1. Actually it means the function does not depend on B. It says the function is 1 whether B is there or B is not there. the function really does not depend on b, it only depends on a and c. So when these merge, we put an entry 1 to indicate that the function depends only on the value of a and c, it does not depend on b, right. Then go to this, again similar to what we had earlier, but come to this, it says the function depends on the value of b being 1. If the b value is 0, the function goes 0, whereas in the other case the function was not depending on the value of b, whereas in this case it depends on the value of b, the value of b matters. So when this folding takes place and this merge with this, that means we have to enter the corresponding cell b to indicate that the function depends on the value of b. Okay. Now how do you arrive at the function? Now we have a reduced corner map, and this is similar to what we had here. We have some variable entered, right? Now how the variable, what the variable is doesn't matter, let's not worry about it. There is some variable. So the way to develop a function from this is, we must arrive at the same function, no? Good. It says the algorithm, I would just state and then proceed. It would say wherever you have 1, okay, there can be more than ones even in the reduced corner map, it all depends on. Wherever you have 1, encircle them separately and then write out that particular term. What is the term here? It says this is true for a being 0, c being 1. In other words, a bar and c, that's what it says. The function should be true when a is 0, c is 1, that is a bar c is true. Then that's all. There so happens the sample or example we have taken is only 1. Now they have another entry b. Like this, if you have other entries of b, you can combine them together. And what about this entry? This entry actually means hardly matters. This does not depend on the value of b. A 1 here means it does not depend on the value of b in the reduced corner map. So we can as well include that. Okay. In other words, we can, while encircling, we can as well include this, mainly because 1 means does not depend on the value of b. So it's a don't care as far as b is concerned. So then we find when you encircle, this encirclement causes the next term or yields the next term, which says c, because the whole thing is c being 1 and b must be there. Okay. Yeah, 1 here means b can be 1, b can be 0. Now we are forcing b to be 1. So b, c is the other term. So this is how you arrive. So a bar c or b c. Now we have got the function from both. The same thing we have to do here too. That is, what is a sa value? See, there are no ones here, right? No one, so we don't have to bother. What we find here is just one thing, and then there is a don't care. Zeros cannot be included, that's like the empty ones there. So this is an encirclement. Okay, take this encirclement and then develop the function as yc bar and b. That's what it means. yc bar and b. Similarly, ra, okay, here yc bar and b bar. Like this can do for the other thing also. SB is, what's it? We have this encirclement, yj and yc and a bar and rb yk and yc and a. So we have arrived at the input functions for the memory elements which implement the state variables a and b. We started with SA bar or A bar latch or SA or a SR latch, and so we are developing the equations for that input.